At very low temperatures, some substances show large-scale quantum effects. Examples are the superconductive metals and superfluid helium. The liquid phase of the abundant isotope helium-4 is superfluid below 2.17 K. The rare isotope helium-3 becomes superfluid too, but only at a temperature 1,000 times lower. We'll concentrate on helium-4, although in our final sequence we will bring the two isotopes together. At the moment we are looking at superfluid helium-4 resting quietly in a Dewar vessel at a temperature of 1.2 K and a vapor pressure of about 1 torr. Looks bluish in color, but that is because of the illumination. The liquid is really colorless. Although the liquid is being rapidly evaporated by a large vacuum pump, it cannot boil. Superfluid helium is a nearly perfect conductor of heat, so a superfluid bath is always isothermal at constant temperature throughout, and no bubbles of vapor can normally appear anywhere in it. Look at the saturated vapor pressure graph. The superfluid, called helium-2, exists only below T lambda 2.17 K and P lambda 38 torr. Above T lambda it's called helium-1. Its normal boiling point is 4.2 K and its critical temperature 5.2 K. The liquid phase persists right down to the absolute zero. There's no triple point where gas, liquid, and solid are in equilibrium. To reach the solid, one must compress the liquid to about 25 atmospheres pressure. The boundary between helium-1 and helium-2 is called the lambda line, marks a second-order phase transition, one with no latent heat but with a sharp discontinuity in the specific heat. Now, to show the properties of liquid helium, we must be able to see it, but this is not easy. The latent heat of vaporization is minute, so we must exclude radiant heat. We absorb this heat from the light source in a cylindrical tank of copper sulfate solution, as seen in the lower part of the picture. The red is absorbed as well, so the transmitted light is bluish. The surface tension of helium is so small that there is only a tiny meniscus. Finally, the refractive index is so small that one gets little modeling by refraction. To overcome this, we use the copper sulfate tank as a cylindrical lens and focus the light onto a perspex diffuser screen, as seen in the upper part of the picture. This gives a highly non-uniform lighting background, which compensates for the low refractivity to give good modeling of any liquid surface. Let us first examine some of the equilibrium properties, beginning with the lambda transition, the great change that takes place at T lambda 2.17 K. As we reduce the temperature of the bath from the normal boiling point 4.2 K by rapidly pumping off the vapor, the helium-1 boils violently until we reach T lambda, where boiling suddenly ceases as we enter the superfluid phase helium-2. Now we watch it. The liquid's boiling quietly at 4.2 K, as we see from the gauge on the left. There's a nichrome ribbon heater in the bath, which we will use later. We're going to open the valve to the pumping line rather quickly, so the liquid will boil violently and the pressure and the temperature will drop rapidly. Bubble's getting larger now. The temperature drops. Remember T lambda about 2.2, just under that. Getting close now. There we go, superfluid. Sudden stop to the boiling. Transition is sharp to a micro K. Now we reverse the process. Warming up with 2 or 3 watts in the heater. Boiling will start around about the heater. There it goes, above T lambda. We've lost superfluid, back in helium-1. Let us see how the density of the liquid varies with temperature. The density itself is low, about 1/7 that of water. The maximum at T lambda, declining slightly below it, but it's above T lambda, it drops by about 15% by 4.2 K. This seems a big rate of change, but in terms of reduced temperature, T by Tc, it's about the same as in other liquids. We can illustrate these things in an unusual way. If we start with a bath at a temperature below T lambda and warm it up with a heater in the middle, being superfluid, the bath warms uniformly to T lambda. After that, only the liquid above the heater goes on warming to 4.2 K. The rest stays cold at T lambda. So we have a sharp temperature boundary, which is a sharp density boundary, and therefore a refractive index boundary. And we can make this visible as opalescence with suitable lighting. put a folded nichrome ribbon heater in a horizontal plane, and we look straight through the bath with the beam of light focused so as to show up the interface, which appears as a waving dark band. The interface waves about because of the turbulence created by the repeated bursts of heat and violent boiling in the upper part of the bath. Remember that the upper part's at 4.2 K, while below the interface it is at T lambda, 2.17 K. Sometime later, the interface has moved down a further centimeter, but is still very visible in spite of the turbulence created by the burst of boiling, and in principle it must remain stable. Now go back to fundamentals. Helium-1 is a nearly classical liquid, but helium-2 is dominated by quantum physics. It's called a boson liquid because, being even-numbered in the nucleus, 4, it obeys Bose-Einstein statistics. We can describe it as an intimate mixture of two fluids, superfluid density ρS and normal fluid density ρN. ρS can move without friction, carries no entropy, and it comprises the whole liquid at absolute zero. Above 0 K, ρN appears, embodying all the thermal excitations and the entropy. ρN increases with rising temperature, while ρS declines and vanishes at T lambda. The first measurement of ρS as a function of temperature was made by a torsion pendulum as on the left. The bob was a stack of thin metal discs separated by the depth of penetration of a viscous wave. For low disk velocity, this was 170 microns. ρN was thus held fixed to the discs, and when full of ρN, the period was given by the moment of the discs plus liquid. But when the spacing was entirely filled with ρS, it slipped over the discs, staying fixed in space, so the period was given by the moment of the discs alone. The difference in period, full to empty, was only a few percent. What we've done to improve things is shown on the right. We've made the bob a spiral of Melinex, 6 microns thick, and open at both ends, with the spiral gap again nominally 170 microns, but actually 190. ρN will be trapped by the spiral and go round with it, but ρS will slip, so the spiral will oscillate as though it were empty. The ratio of moments, full to empty, was 2.2, so the ratio of periods, the square root of that, was 1.5. The actual periods were 2.8 and 1.9 seconds. This is the spiral. The Melinex strip was 1 meter long, 6 centimeters wide, and as we said, 6 microns thick. It contained 20 turns, inner diameter 10 millimeters and outer diameter 18 millimeters. You see the structure of the spiral more clearly looking at it end on. It's really very uniform. You see 1 or 2 paper shims which we had to use to keep the spiral winding true. The spacer ribbons were 0.5 millimeter wide, and they were a bit troublesome as well. It's all tacked together with nail varnish, and although it looked stable, it was extremely fragile. The spiral is mounted in its frame and hanging on a quartz torsion fiber. The fiber is shining brightly by reflection. The spring at the top acts as a shock absorber to keep accidental jars from causing disaster. Supporting control rod can both orient the frame in the Dewar and rotate the spiral independently of the frame. Now we have the spiral in the bath, temperature T lambda, and therefore full of normal fluid. We started by rotating the support, which you're going to do just now. There we are. Wait for it to settle, then swing it back. Period is just under 3 seconds, heavily damped both by external drag and internal because the spiral came out a little too large in spacing. We repeat it again to fix in our minds the 2.8 second period. Let's swing it back again. There it is, very heavily damped. Now we're going to cool the bath to 1.2 K. There we are, 95% superfluid. This time the period is 1.9 seconds as in a vacuum. It's much faster than before. The amplitude decays at first due to external drag, but also because the linear velocity in the spiral exceeds the critical velocity for onset of friction, which is only 1 or 2 millimeters per second with this spacing. But at small amplitude here it will swing for many, many minutes. For comparison, we take a look at the spiral oscillating in a vacuum. Period again 1.9 seconds, as it was in pure superfluid. Naturally no decay here. Now we're back again in the bath at 1.2 K, close up, still swinging at 1.9 seconds period. Now we're going to go back to T lambda. There we are, with only rho n in the spiral and the period again 2.8 seconds, as we shall see in a second or two. There we are. The nature of the superfluid is most evident in the transport properties, and the two-fluid model of rho s and rho n gives a good description of these. Take heat transport. The flow of heat is accompanied by mass and momentum transfer. In figure A, a temperature difference means a difference in chemical potential. The gradient of the chemical potential drives rho s towards the heat source, where it's converted to rho n, which then must move down the temperature gradient. This sweeping of rho n is sometimes called a heat flush. What results is a kind of superthermal conductivity by forced convection. Hot and cold are relative terms here, close to the absolute zero. Now look at figure B. We filled the thermal channel with what we call a superleak, a kind of plug which permits flow of rho s, but which blocks the viscous rho n. Rho s is still driven up the temperature gradient, but since rho n is blocked, this creates a level difference, with the hot end standing higher. If the heat flow and superflow are large enough, the hot end overflows in a fountain. Now such a fountain is thermodynamically reversible. It's therefore a heat engine, a device for converting heat into work, the simplest one can imagine, with no moving parts. Being reversible, it can be run also as a refrigerator. You can see this in figure C. Superfluid flows through the superleak, leaving rho n behind, but rho n contains all the thermal energy, so the top stays warm. Rho s is essentially at absolute zero, so the bottom vessel cools, and this is a refrigerator. To show the fountain at best advantage, we designed the vessel as in figure D. Superleak is at the bottom, emery powder held in by silk cloth. With the heat on, superfluid rushes in through the superleak and spurts out of the orifice at the top in a fountain. This is the fountain tube we shall use, 2 centimeters in diameter and 5 centimeters high. You see the 320 grade emery powder at the bottom. The electrical heater is a spiral of nichrome ribbon. Now the fountain tube is in the bath at 1.2 K. With the heat input of half a watt, we get a fountain 5 or 6 centimeters high. We could produce a fountain 30 or 40 centimeters high, but it would be very wasteful. Fountain is not very efficient. Only about 1% of the heat goes into the kinetic energy of the liquid. The rest goes into warming the bath. With a carefully shaped orifice and with a low level of heating, we can produce a fountain showing pure potential flow with no turbulence or secondary flow. The falling jet spreads out into a nice bell-shaped canopy, different from the paraboloid we have just seen. We vary the heat input, which makes the fountain height vary here. The bell shape arises because the canopy liquid is warm and traps warm vapor under it. The warm vapor is at a higher vapor pressure, and this is sufficient to blow the canopy out to that shape. Since the surface tension is small, once the canopy is formed, there's nothing to cause it to break up, so it remains intact. We move the camera in for close-up, and we try to stabilize a nice fountain. From the size of the orifice and simple geometry, it follows that the canopy is only 50 microns thick where it touches the bath. Most orifice shapes do not produce such bell canopies, and we had to try half a dozen before we achieved success. Though the real nature of the correct design is still a bit of a mystery, the result is certainly elegant. We're playing around here with the heating to give varying fountain heights. To our astonishment, the fountain performed well even when totally submerged. Only superfluid can enter through the superleak at the bottom, but both normal and superfluid can enter the top orifice with equal ease. In spite of this, the flow is dominated by superfluid coming through the superleak to give a fine submarine fountain. We're going to watch the disappearance of the fountain as we go up through T lambda. The fountain is only about 2 millimeters high here because the temperature is about 2.1 K, superfluid fraction very small. Getting closer now. Fountain only a millimeter or so high. There it goes. No fountain helium-1, only boiling. Our final fountain shot is with a smaller fountain tube at 2.0 K to show the bell blown out so much that it enters the bath nearly horizontally. This is because at the higher temperature the vapor pressure is greater, with a smaller tube the canopy is thinner. Now we want to examine superflow through a superleak. We will use a vessel like the one sketched with the plug made of tightly packed jeweler's rouge. Such a plug is practically impermeable to all other fluids, liquid or gas, but it offers no hindrance to rho S. As we said earlier, such superflow is a kind of refrigerator, since the heat is held back by the plug, which lets through only the cold superfluid. Indeed, we can make such a fridge, which, starting at 1.2 K, maintains a bath at 0.8 K, a big relative drop in temperature. This is the vessel, about 2 centimeters in diameter and 8 centimeters high. The rouge was hammered in a little at a time while the vessel stood in a dish of frozen mercury. When the mercury melted and ran out, it left the plug in place. The interstices between the rouge particles was probably of the order of a few hundred atom diameters. We put a heater in the vessel so we can produce a fountainhead if we wish. Now we put the vessel in the bath with the temperature somewhat above T lambda. Nothing is coming through the superleak because the vessel contains helium-1, which is viscous, with a viscosity similar to that of the air we breathe. Beginning to pump steadily, dropping the temperature towards T lambda and pressure of 38 torr. See occasional bursts of boiling in the tube. Now close to T lambda. There we are. Helium-2, and the rouge plug slowly starts to leak. Slowly at first, then faster as the temperature falls and the rho S fraction increases. You can see the liquid dripping from the bottom of the rouge plug. Now we're at the lowest temperature, 1.2 K with 95% superfluid. We submerge the vessel, then raise it and let it empty. It empties through the superleak as though it were not there at all. We repeat the process several times because it's rather dramatic. It's important to note the difference between superflow and viscous flow. In viscous flow, the rate of flow is proportional to the pressure head. So if our flow were viscous, the rate of flow would drop to 0 as the liquid level reached the rouge plug. With superflow, the rate is independent of driving pressure, so the liquid level drops at a constant rate. Now we want to make the vessel act as a fountain pump. We put some heat in to produce a small delta T and a small fountain head. Delta T here is about a millidegree or so. Turn off the heat, drops it again at a constant rate. Put in a bit more heat, head rises at the same rate as before, but goes higher. And finally spills over in a small fountain before again subsiding when we turn the heat off. Now, since Superflow is frictionless, a mobile film of the liquid moves swiftly to cover all surfaces connected with bulk liquid so long as they are below T lambda. Film thickness is determined by a balance between van der Waals force and gravity, and is about 100 atoms thick at 1 centimeter above the bulk liquid. Film contains the correct ratio of rho n to rho s for its temperature, but rho n is held fixed by viscosity, while rho s moves through it at a critical velocity of about 30 centimeters a second, which is practically independent of the length of path and of the driving pressure. To show this, we are going to use a small beaker like the one sketched. Film is pulled down the outside by gravity and replenished from inside, and it drips off the bottom at a constant rate until the beaker is empty. The actual beaker, 17 millimeters diameter and about the same height. The copper rod underneath dips into the bath and helps to keep everything at bath temperature. With a film only 100 atoms thick and a minute latent heat, we must be extremely careful to exclude thermal radiation. To do this, we enclose the beaker in a housing with heat-absorbing glass windows. Now the beaker is in the Dewar, just above the bath and at a temperature above T lambda, so there are no drops. We'll open the valve to the pumping line so as to reduce the temperature. Drops will only begin to form when we get a little below T lambda, because while cooling we have not got thermal equilibrium. But there we are, starting to drip. Slowly at first, because of the small superfluid fraction, but getting faster as the temperature goes down. Here we are at 1.2 K, where the superfluid fraction is greatest, and therefore where the dripping rate is a maximum. We're going to shine warm light from a 60-watt desk lamp onto the beaker in order to burn off the film and stop the drips. Light's coming up now. Film is burnt off and drops cease to form. Take away the light, beaker surface cools again, and dripping recommences. Still at 1.2 K, while the mobile film is unique to helium, films are not. Van der Waals forces act on all atoms, so all wetting liquids attempt to form films. They mostly fail, either through viscosity or evaporation, or both, but given time, some oils and such like do form films. Now we want to show by another means that we really have a moving film. Consider the narrow beaker shown here. In isothermal conditions, the driving force is gravity. If there's a level difference between beaker and bath, the film will move so as to eliminate it. Film has inertia. It overshoots the position of rest and oscillates about it in simple harmonic motion. But with such a simple beaker, the moving mass of the film is minute, the amplitude of oscillation is less than a millimeter, while the period is about 90 seconds. Not very dramatic. Fortunately, we can improve things. We can keep the observation tube very narrow, say 1.5 millimeters in diameter, as the central standpipe here, and make the potential energy change, the amplitude occur in it, while we increase the mass of the moving film by having two large side arms carry the film. We thus increase the inertial element by a factor of about 50, which increases the total swing to 5 or 6 millimeters and decreases the period to about 20 seconds. To make the system work, we must avoid bulk liquid in the side arms in the oscillation range in the standpipe, that is, above the lower of the two paint spots which mark the operating range. To ensure this condition, the side arms carry glass stoppers carefully ground into them with rouge to have a clearance of less than a micron. In the stopper region, only superfluid can pass, so we're okay. This is the apparatus. The standpipe and the side arms enter large copper chambers which are connected together. They have a large surface area so as to give good heat transfer between the liquid inside and outside. The need for this will be explained in a moment. The big dead volume inside the chambers has naturally no effect on the oscillation. Stoppered region in the side arms can be clearly seen because of the residual rouge staining. You can also see the two paint spots on the standpipe. We must not allow thermal radiation to fall on the side arms, so we enclose them in copper shields to protect the standpipe with heat-absorbing glass front and back. Everything's now ready for the Dewar. Now it's in the Dewar with the bath at 1.2 K. The bath level is near the lower paint spot on the standpipe. The meniscus in the standpipe is a millimeter or so above the bath level and slowly oscillating with a small amplitude. Push the apparatus down by a centimeter and watch the meniscus rise to the bath level. And pass it, reach well above it before falling back and going into inertial sinusoidal oscillations. Total swing of the first oscillation is 5 or 6 millimeters. We are watching it in real time. Note that the position of rest, the center of the oscillation, is about a millimeter above the bath level. This is a capillary rise due to surface tension, which is exerting a constant upward force in the standpipe. Remember that the oscillations are caused by the kinetic energy of the superfluid in the film going in and out over the rims of the side arms and being converted into potential energy of the bulk liquid in the standpipe. Remember also that since it is only superfluid that's moving in the film, and that superfluid carries no entropy and is therefore by itself at absolute zero, the bulk liquid at the downstream end of the film tends to cool, while that at the upstream end tends to heat. Poor heat transfer path between the reservoirs at the ends of the film would mean slow thermal relaxation between them, and this would constitute a potent source of dissipation of film energy and quick exponential decay of the oscillations. That's why we use the large copper vessel to hold the side arms and the standpipe, to provide about 50 square centimeters of thin copper wall between bulk liquid at either end of the film path. This gave such good heat transfer that the whole oscillating system was essentially isothermal, with consequent small dissipation and small decay. So small, in fact, that as you can see, the amplitude has only dropped to half value after about 6 swings. The system is so good that whenever we looked at it, it was oscillating. We never managed to see it completely at rest. Unique to the superfluid is second sound. First, or ordinary sound, consists of density waves with all parts of the medium moving in phase. In an organ pipe, the standing waves have nodes of pressure. In helium-2, normal and superfluid can be excited to move in antiphase, with the density constant. This is second sound. It's generated by an AC heat source, and the nodes are of temperature. We can demonstrate either first or second sound with a Rayleigh disc in an organ pipe. The disc is suspended elastically at 45 degrees to the axis at an antinode, where the velocity field produces a Bernoulli torque, which tries to turn the plane of the disc normal to the field. Torque is a maximum with the disc at 45 degrees, and is proportional to the square of the velocity. On the left is a schematic half-wave organ pipe. An AC heater at one end produces at resonance standing waves of second sound. Our half-wave pipe is on the right, made in 2 halves so that we can stretch a fine quartz fiber across the middle, holding the Rayleigh disc. At the bottom is a nichrome ribbon heater. Second sound is a velocity at 1.2 K of about 20 meters per second. A half-wave tube, 10 centimeters long, will thus have a fundamental of 100 hertz. That is 50 hertz AC, since we get 2 heat pulses per cycle. The first harmonic, 3 halves wave, that's 150 hertz AC, and the second harmonic, 250 hertz AC, gave the best responses due to higher normal fluid velocities. This is the organ pipe with the heater at the bottom. The Rayleigh disc is a 5 by 10 millimeter piece of paper. Since at 1.2 K, rho S is 95%, to keep the total rho constant, at the antinode, rho N must move 20 times as fast as rho S. So the square of the normal fluid velocity will really provide all the torque. There's a numeric display beside the Dewar to show the AC frequency of the heater. We examine the folded nichrome ribbon heater. Probably had a thermal relaxation time of at least a millisecond, and that may have been the thing that kept us from seeing the third harmonic with its heat pulse frequency of 700 hertz. This is the Rayleigh disc in close-up. You can just see the quartz fiber. When I blow lightly on the disc, we get an idea of its frequency of about 2 hertz, and hence the sensitivity. Now the half-wave organ pipe is in the bath at 1.2 K. The LED numerals on the left indicate the AC frequency. Heat pulse frequency is double that. We're going to posit the fundamental just below 50 hertz. Watch for a vane movement. Go up and down 2 or 3 times, but the vane only gives a small twitch each time. Very tiny twitch. Now we go up to the first harmonic, up and down through it at about 150 hertz. The response is better here. Up and down through it 2 or 3 times. Vn is trebled here, so the torque will be 9 times as great. Difficult to stay on resonance or even go slowly through it. Really very sharp. Now second harmonic. Very good response here. Third harmonic, we didn't really see anything. Pulse frequency probably too great for the heater. Now we're in close-up, staying near the first harmonic because the response was good and the control was reasonably easy. There you see, very good response. Going up and down through resonance. Very high Q value for the organ pipe. Managed to stay on resonance very well there. Near the heating limit. About half a watt there. About a few seconds later, after the end of this shot, we blew all the liquid out of the tube with a little more heat. Finally, we're going to examine the behavior of a liquid mixture of the 2 isotopes, helium-3 and helium-4. Above about 0.8 K, helium-3 behaves very much like rho n in its relation to rho s in superfluid helium-4. Below 0.8 K, things are different. There, minimizing the free energy of the system requires the mixture to separate into 2 isotopic liquids, the only phenomenon of its kind in nature. We're going to cool a liquid mixture of equal amounts of helium-3 and helium-4 down from 1.2 K to about 0.3 K, and watch it separate into a liquid of about 97% pure helium-3 floating on a liquid of about 88% pure helium-4. Except for 6% of helium-3 which remains dissolved in superfluid helium-4 at absolute zero, the separation is complete. The 2 liquids have a visible surface of separation between them with a 1% difference in refractive index and a tiny surface tension. The graph shows equilibrium states, but although cooling is non-equilibrium, the superfluid nature of helium-4 allows the separation to be very rapid, so departures from equilibrium are small. Thus we've drawn the yellow lines of the 2 phases close to the region boundaries. The sunburst effect on the horizontal part points to an unusual phenomenon seen here not on cooling, but on subsequent warming, when the last small volume of helium-3 has suddenly to coalesce with the rest of the mainly helium-4 liquid as the temperature rises. This happens violently, as we shall see. This is a replot of the previous graph to show the liquid fractions as a function of temperature. A beaker of the separated liquids is sketched on the right. Not only is liquid helium-3 less dense than helium-4 because of its smaller atomic weight, but notice that it occupies more than half of the total liquid volume. This is a visible manifestation of the concept of zero-point energy, which says that at absolute zero, atoms are not completely at rest, but have a residual kinetic energy which is inversely proportional to atomic mass. We see it in helium because no other element remains liquid down to absolute zero, and the atomic masses are small. Zero-point energy blows up the molar volume of liquid helium-4 to 3 times its classical value, and the molar volume of liquid helium-3 to 4 times classical, hence what we see. Since we will steadily cool the liquid, we will steadily track along the separation curves in time, hence the time ordinate at the top, where the surface of separation, the 3-4 interface appears. It will drop rapidly at first, and then more slowly as the temperature falls. This is the sketch of the apparatus. At the top is the gas container, a stainless steel chamber with a glass viewing tube below it, filled at room temperature to 40 atmospheres pressure, 20 atmospheres each of helium-3 and helium-4. To give about 1/3 of a cc of liquid when all the gas is condensed. The cooling is done by adiabatic demagnetization of ferric alum. The base of the viewing tube is penetrated by a copper cold finger which comes up from the copper frame which holds 4 cylinders of the salt, which 2 are sketched. Sieved granules of salt are mixed with a little tap grease and then highly compressed into stainless steel tubes. Each tube is threaded by many copper wires to give quick heat transfer between the salt and the cell above. The salt and the cell are in a vacuum chamber, while the superconducting solenoid around the salt is in the helium bath at 1.2 K. Running a solenoid current up to 20 amps gives a field on the salt of 1 Tesla, which warms the salt to about 2 K and boils off the helium-3. After it is cooled back to the bath temperature and the helium-3 is recondensed, the system is isolated and the salt demagnetized, making it cool to about 0.3 K. This condenses the remaining helium gas, after which separation takes place. After demagnetization, the system gradually warms, the 3,4 interface rises, and finally bumps the top liquid surface as the remaining isotope fractions violently mix. We're going to look briefly at a close-up of the 3,4 cell, with the copper cold finger at the bottom of the viewing tube and the sealing clamp on the filling capillary at the top. This is the cell assembly. The 4 salt tubes are 11 centimeters long. The glass viewing tube is 4 centimeters long with a 4 millimeter inner diameter. The cell is in its vacuum case in the cryostat mounting. Superconducting solenoid is in place but without its folded copper foil leads. Also still to go on is a radiation shield over the cell housing with narrow windows of heat-absorbing glass. Further, to reduce radiant heat, we use this large diameter copper sulfate tank, and we focus it directly on the viewing tube, but here it is defocused to show up the apparatus. This is the viewing tube with the liquid mixture being cooled. Demagnetization of the salt is complete and the very cold salt is draining heat from the liquid via the cold finger at the bottom. We begin to see disturbance around the finger with helium-3 separating and mixing again. The disturbance is going to reach farther and farther up the tube till we get to the top, and the interface retreats down the tube with increasingly rich helium-3 above. Settling below the middle. Now we're going to watch the liquid warm up. We take short shots every few minutes as the interface rises to see it finally violently bump the liquid surface. Pay no attention to the flash before each shot, it's just the camera accelerating. There it goes. We're now going to show briefly what happens when we magnetize the salt. The heat boils off most of the helium-3, which must then recondense before we can demagnetize. Here's the separation sequence again, this time after a very big demagnetization from 30 amperes, 1.5 Tesla. Strong cooling now, disturbance rises quickly, the interface falls. The speed of separation is really remarkable. It's worth noting that the only significant difference between the isotopes lies in their nuclear spins. The boson helium-4 has spin 0, while the fermion helium-3 has spin 1/2. The cell here is probably getting down to 0.2 K to give very complete separation. The 3,4 interface is far down the tube, below the middle, so we can really see the effect of zero-point energy on the molar volumes. The reason why it goes on bubbling down below is because the liquid helium-3 above is warm and is also a poor heat conductor. It can only lose heat by evaporating helium-3 gas down in a heat flush to the cold finger to condense into buoyant globules which rise to the interface to burst and send clouds of steam-like droplets of very pure helium-3 into the less pure upper phase. We bring our film to an end with a final shot of the liquid warming, with the separated helium-3 and helium-4 phases violently collapsing together. If you watch carefully when the collapse occurs, you can see momentarily the turmoil shoot right down through the liquid. One gets an idea of the minuteness of the surface tension of the 3,4 interface by its extreme flatness, with no discernible meniscus, even though the tube is only 4 millimeters in diameter. Now watch for that dramatic collapse. There it goes. Collapse of natural isotope separation, the only phenomenon of its kind in nature.